So in this video we're going to look at how to solve trig equations that have non-standard periods. Now the first thing I wanted to mention is if you ever see a trig equation like this, your first step you always want to have be isolating the trig function. So in this case that would mean subtracting 1 from both sides, and then we'd have 4 cosine 2x equals 2, divide both sides by 4, and then we'd have cosine 2x equals 1/2. And so you want to get a cosine, the cosine or trig function by itself on one side equaling a single number. That's always going to be the place you want to start. So now let's look at a equation like this. Now, so the approach that we're going to use in this video is called substitution, and that means we're going to take this stuff here and replace it with another variable. I'm going to use u. It's just a very common variable to use for substitution. So I'm going to let u equal cosine, u equals pi over 4x. And so then my equation becomes cosine of u equals 1/2. And now we can solve this just like we have any other cosine function or any other cosine equation, which means we can do things like look at the unit circle and say if the cosine value, the x-coordinate is 1/2. What are the angles? I happen to know this one. This is a special angle, and I know that two of my solutions are pi over 3 and down here 5 pi over 3. Now, in some cases we may want more solutions than just these two. It would depend on what interval we're solving on here. And so there's a couple ways we can handle that. One way is to just start out by writing out all solutions. And so if we wanted to write out all the solutions, we could do so by saying pi over 3 is a solution, and for a standard period, if I add any multiple of 2 pi to it, I'll also get a solution, because if I add full rotations I get coterminal angles. The idea here is that k is representing any whole number or integer constant. And then of course 5 pi over 3, add any number of full rotations will also give me a solution, right? And those are my u values. Now remember though, we're not actually trying to solve for u, we're trying to solve for x. And so now that we have all of our solutions for u, we can go back and undo our substitution. We can remember that pi over 4x is equal to u, pi over 4x is equal to u, and now we can solve this equation here for x. So how would I solve this for x? I can solve this for x by multiplying both sides of the equation by 4 over pi, right? Because that'll cancel out there. We'll do the same thing down here, 4 over pi, multiply all of this by 4 over pi, cancels out here and here. And so in this top one here, I'm left with x equals, right, because all my constants canceled out there, x equals. And now if we distribute our 4 over pi, the pi's will cancel and we'll be left with 4 over 3 plus, multiply this times this, the pi's cancel and I'm left with 8k. And here, if I multiply this through, 4 over pi times 5 pi over 3, again, the pi's cancel, I end up with 4 times 5 is 20 thirds. And again, multiplying that, we end up with 8k. And there we go. These are all the solutions for x, which means now if we actually wanted to start writing out some specific solutions, my first solution is 4 thirds. My second solution is 20 thirds. My third solution now would come from going ahead and letting k equal 1. So now if I let k equals 1, then I'm going to add 8. So my third solution is going to be 4 thirds plus 8. Or in other words, 4 thirds plus, what is that? That would be 24 thirds, right? So plus 24 thirds is 28 thirds is my third solution. My fourth solution is going to be my second solution here plus, again, one full period. So we end up with 20 thirds plus 24 thirds is 44 thirds. There's solutions 1, 2, 3, 4. If I wanted a fifth solution, it would be 4 thirds plus, now I'm going to let k equal 2. So instead of adding just 8, I'm going to add 8 times 2. I'm going to add 16. And if I do that, that's going to be, what, 4 thirds plus 24, that would be 48 thirds is 52 thirds. That would be my fifth solution. I could add 16 to this to get my sixth solution. I could keep on going for as many solutions as I need. And there we go. There's how we solve this using substitution. Now, in this case, we used the plus 2 pi k here. We could have instead just listed out, like let's say we only needed 4 solutions here. We could have just listed out the next 2 solutions for u and multiplied all of those by 4 over pi, but this is a nice sort of general way to handle this type of problem. All right, let's try one more. Sine of 3x equals 0.7. So we're going to do the same thing here. We're going to use a substitution. So we're going to let u equal 3x. So we're going to write sine of u equals 0.7. And we'll go ahead and we'll solve this the usual way. U is the sine inverse of 0.7. Sine inverse of 0.7 is, in radians, 0.7754 roughly. And then we need a second solution, because that's my first solution. My second solution then, again, I'm going to go to the unit circle here. I'm going to say my sine value, my y-coordinate is 0.7. My first solution is here with an angle of 0.7754. My second angle with the same sine value will be here. And I can think of that as forward by pi, back by the same amount that we had here. And so this angle here will be pi back by 0.7754. Oops. 54, and that will be about 2.3662. All right, and now we have ourselves 2 solutions, and you can see that any other solutions are going to have to be coterminal angles. In other words, we're going to have to add a full rotation. So if I wanted all solutions here for u, they would be 0.7754 plus any number of full rotations, or 2.3662 plus any number of full rotations. All right, so again, we figured out what our all solutions for u are, but now we need to go back and find what x is. So we're going to use the same approach we did earlier. We're going to say u is equal to 3x. So this is equal to 3x, this is equal to 3x. Let me write it again up here. So we got 3x equals 0.7754 plus 2 pi k. We've got 3x equals 2.3662 plus 2 pi k. And now we need to solve each of these equations for x, which as you can see we'll do by dividing by 3 on both sides, or multiplying by 1/3 if you prefer. So on the top here, we're going to get x equals, so we take 0.7753 or 54. If you still have the exact value on your calculator, use that instead. We'll divide that by 3 and we get 0.2585 roughly. And then we divide this number by 3 as well, so we get 2 pi over 3k. Or 2/3 pi k, however you want to write that is fine. And then this one, we end up with x equals, let's see, I had 2.366 divided by 3. That ends up being about 0.7887. After dividing that by 3, divide this by 3, I get plus 2 over 2 pi over 3 Okay, and once again, this describes all solutions. If I wanted some specific number of solutions, say 3 or 4 solutions, I could just start out with these two as my first two solutions, and then I add 2 pi over 3, 2 pi over 3 to this one, then 2 pi over 3 times 2 to each of them, 2 pi over 3 times 3 to each of them. Just to be clear on what's going on here, notice that with this function, the period is 2 pi divided by b, so it's 2 pi over 3. So this number that we're adding is periods. Essentially, we're adding full rotations or full periods to those first two solutions to come up with more solutions. Okay, and so that's the idea of how we can solve trig equations with non-standard periods using substitution. Let's look at one more involving tangent. All right, so let's solve tangent of 1/3 x equals -4. So we'll do the same thing. We'll call this u, so that we've got tangent of u equals -4. We'll go ahead and do the inverse tangent to come up with our first solution. And the inverse tangent of -4 is -1.3258. Now, if we were looking for solutions, say 0 to 2 pi, this solution's not going to be in that interval, but we don't really need to worry about that. Everything will work out okay in the end. So now let's talk about all solutions. Now, with tangent's a little bit different than sine and cosine, because if we have an angle here, this is an angle, let's say -1.3258. Then another angle that has the same tangent is the angle that has the same slope as this, and that is this angle here, which you'll notice is different by pi. Tangent, the standard tangent function, has a period of pi, and so it turns out that we can describe all solutions here by just taking our first solution and adding multiples of pi to it. Makes life a little easier than the sine and cosine, where we need to find a second unique solution first. Now that we have that, we can go ahead and say, undo our substitution. We can say 1/3 x equals -1.3258 plus pi k. In order to solve for x, we can multiply both sides by 3. And we'll end up with x equals, let's see, if I multiply that number by 3, I get -3.9775, roughly, plus 3 pi k. Now, if we wanted, say, the first 3 positive solutions or 2 positive solutions, well, this solution's not positive, so we wouldn't bother including it. But if we let k equals 1 here, we would get, let's see, 3.977 plus 3 pi. If we added, so if we do -3.9775 plus 3 pi, we end up with 5.4473, and that would be our first positive solution. If we then let k equal 2, so we had 3.9775 plus 3 pi times 2, or 6 pi, and we end up with 14.8721. That would be our second positive solution, and we could keep on going if we needed more solutions than that. Okay, so there's an idea of how we can solve trig equations with non-standard periods using substitution.